I'm Lyes Kahouadji, head of chemical engineering at Imperial College, and I'm going to present the recent development and also result that we've been doing in domain of numerical simulation of multiphase flow in the presence of surfactant. First of all, I would like to introduce the team, and here my left is my supervisor, Professor Omar Matar, Professor Richard Craster from the math department where we've been collaborating, and also like three other colleagues from France, Damir Jurik and Jalal Shardi from French lab, LIMSI CNRS, and Sungwon Shin from South Korea. And those people and myself, we've been in a long time developing this code blue, and most of the result that I'll be showing, it's really, I'll say the technical material of this code with surfactant. You can see it in this article. So I would like also to introduce two fantastic students, actually. So this work that I'll be presenting, it's not only myself, but it's also the students that I've been supervising the last 3.5 years. You have Hasan Bachvarov on the left and Ricardo on the right. And here in the bottom, all the articles that has been accepted, and some of them it's still under review. All of this have been it is the work of this year. So most of the result, so not only the development but the result I'll be showing, you can see them in this reference. So the topic I will be showing, so first of all, talking about the code, but also the multitude of application and multi-scale that can be applied in it. So you have retracting ligament, the jet flows, the falling film, bursting bubble, elongated bubble, and all of this, it has really all those topics, we make them like in general, especially for the jet flow, and then we try to isolate mechanism. When you see this example of jet flow, it occurs a lot of singularities, coalescence, pinch-offs, and then we try to isolate mechanism and then do them one by one through bursting bubble, a coalescence example, and then a film. Of course, when we deal with surfactants, so you really need really robust code. You really need a robust code able to simulate multi-scale and all phenomena. So we have this code, we call it the code blue, and it's a parallel solver. It runs, it solves the Navier in both ways, and then it tracks the interface with the front tracking technique. So we are able to go through really high density ratio up to 100,000 of density ratio, and also and more than 1 million of a viscosity ratio. So it's an Eulerian grid for Navier-Stokes equation, Lagrangian grid for on the interface, and of course everything it's parallel. It can be run in a simple laptop, as you can see here. It's an example just of a drop impact in a pool, or with an HPC supercomputer here, for example, a drop impact, and then it's a splash a configuration using 4,000 subdomains. And here are the subdomain in the top, the subdomain decomposition. The addition of surfactant, it's quite complex. So as I said, we use the Navier-Stokes equation, and then there is something particular. So you have a normal component, like a normal advection for the interface. Here it's the normal force, and then you have a tangential force that needs to be added, and this is due to the variation of the surfactant along the interface. And surfactant are chemicals molecules, so you have concentration of particles. So you have to solve at the same time transport equation in the bulk and another transport equation on the interface. And here are the two equations that need to be added. So here in the bulk and here in the interface, C, it's the surfactant concentration on the bulk, and gamma, it's surfactant concentration on the interface. And there is also communication between them in the bulk and the interface through a source term. This source S, it has this type of formulation. There is a part linked to the adsorption and another part which is desorption. When you have more concentration on the interface or on the bulk, so will be an exchange from the interface to the bulk. And here it has to do with this type of exchanging and varying two key parameters, which is the adsorption and the desorption. And of course, when you have variation of the interfacial concentration on the interface, it will give you a non-uniform, so it will give you also a variation of the surface tension on the interface. So the surface tension will be locally. And how we do this, when we compute the gamma surfactant concentration on the interface, we use the Langmuir equation of state, which is like this. And here the local surfactant, the local surface tension on the interface. It's a function of the surface tension when it's clean without interface, and plus a formulation like this. And the beta S, this is what we call the elasticity number. And it is a really important parameter which gives you the strength of the interface. So here is the same equation again. And as I said, there is, we have the exchange between the bulk, the concentration in the bulk and the interface. It does through this this equation, and all these parameters are here. Adsorption coefficient, Ka, the desorption coefficient. We have also the maximum packing, the gamma infinity. This is what we call the maximum packing, and it is the maximum of concentration that the interface is able to handle. And there is also the adjacent Cs in this formulation. It's the bulk surfactant immediately adjacent to the interface. So for example, here, I did this drawing. This is the entire domain. The red is the interface. And here it's one phase, and the white it's the other phase. And CS, so it's a scalar, so it's in the middle of the cells. And this is where CS are, so they are needed. And of course, for this, we have some operators. They're not simple nabla or they're not, it's type of gradient that they are tangential to the interface when we deal with this type of equation. And of course, now in everything we always use non-dimensional. So for when we just use clean interface without surfactant, we usually use Reynolds number, the capillary, or the Weber. So this is highlighted on blue. But the addition of the surfactant, it gives you to a lot of others parameter control. This is the Peckley number, both in the bulk and the surfactant. The bulk and in the interface. DC is the diffusivity of the surfactant in the bulk, and DS is the diffusivity of the surfactant on the interface. And we have also the Biot number, which gives you like the desorption parameter, and the K number, it's a non-dimensional number that give you a ratio between the adsorption and the desorption. This is all type of input parameter you do with your simulation, and the output when you run any simulation, I'll say it's the Marangoni stress. And the way we define this, we go back to this equation of state, and then when we derive, so you have a variation of sigma, and this gradient it'll give you what we call the Marangoni stress. This is the sigma S of sigma. The sigma is the surface tension, a tangential stress. And when we divide by Reynolds time the capillary, it gives you something looks like the Marangoni number. So we define the Marangoni number as the beta S. Beta S is the elasticity, divided by Reynolds and the capillary. Application and motivation. So this work, and I will also say this adventure started, I will say, 4 years ago when I was when I joined Imperial College, and we were collaborating with a lot of industrial partner, and the important industry we were collaborating is Procter and Gamble. And Procter and Gamble, it's all what you see. It's shampoo, washing up, washing liquid, toothpaste, and all of this product has, contains surfactant, especially the washing up liquid. And an industry like Procter and Gamble, so they consume a lot of surfactant, and the way we produce surfactant, it's this type of application we call annular film reactor. So this annular film reactor equals a ballistra type. It's this massive monster, I will say. But when you look inside, it's something that looks like this. You have like tubes, really long tubes, the size of 8 meters long, and maybe 1 or 2 inches diameter, and they inject inside this reactor alcohol fats, and they also inject in gas SO3, which is it's a sulfur trioxide, a sulfur SO3, and it's a chemical reaction. It gives you a surfactant. So in the bottom of this reactor, this is how you get surfactant plus heat, because the chemical reaction occurs on the interface, so it generates heat. And the major problem in this reactor, that sometimes when you have a really thin film, so here it's the shape of the interface that I was doing for Procter and Gamble, and when you have a really thin film, so it will be overreacted here, and it will be overheated. And if it will overheated, the surfactant you will be producing, it will burn. And if it will burn, it will carbonize. And if it will carbonize, the surfactant you're producing is black. And when you have this type of problem, so you have to stop the production because the surfactant is black. And if using black surfactant for the shampoo you are buying, it's really bad business. So if you have this type of problem, you stop the production, and then you have to clear up all the pipes. So it's a waste of money and it's a waste of time. So that's why this is the type of work that I've been doing for Procter and Gamble. I'm afraid I will not expand a lot of talk on this. It's just to show you the application and also the need of using surfactant in the falling film in general. So the first application I've done, and this is the work that has been done carefully with my student Asan Batarov. It's a simple falling film in presence of surfactant. In all the community of falling film, there is this fabulous work of Park and Nozoko, and they were able to provide an experimental work on falling film, but this falling film, it's pulsed. And this is the type of wave and evolution that we provide. And they provide in the articles, and we use also this just to also validate our work, even in a clean situation without surfactant. So imagine, so you take one piece of wave, and we build a domain like this, and it's really and it's a domain which is periodic, and the size of this domain, it's really the wavelength on a streamwise and also on a spanwise. You have a falling film, partially filled with liquid. The gravity is toward the stream, the streamwise. It's a vertical falling film. You have just a vertical plate and water falling across this. And this is on the right, I'll say the initialization of the velocity. So we initially perturb the interface. We could start by a flat, but we initially perturb an interface with the sinusoidal function just to make the simulation quick. And here what we are doing, it's insoluble surfactant. So the control parameter it's the Reynolds number, the number, the Freud number, and for the surfactant, it's the Peclet and the Marangoni. I'm going to show you the simulation. So here, of course, in the left, it's our simulation in the absence of surfactant, and you can see at the equal time. So we obtain similar type of pattern. It's really important, I'll say, qualitative validation. And here what I'm going to show you, it's the evolution of this wave when it is clean. And then when you vary the elasticity parameters, beta S, and for each elasticity, you have a special Marangoni wave. So this is the evolution. Do you see the animation correctly? I hope yes. So this is the evolution, and you can see in the clean you have a lot of big waves and capillary waves. And when you add surfactant, there are many things that change in. First of all is the big elasticity. In the big elasticity, what it does, it's reduce and also kills the capillary waves, and it acts at rigidifying the interface. So, but a smaller elasticity, it's a bit weak to kill this capillary waves, but it kills the span-wise the span-wise perturbation quickly. This is the example. I can show you evolution of the interface, and then it will give this type of periodic 3D waves, and then it will suppress the periodicity in a span-wise direction, and it wouldn't kill all the capillary waves, but it will keep some of them, but they were reduced a bit. But when you have even smaller elasticity number, and this is, I'll say, the major result of this wave. So the elasticity is so weak, so it will take a time to kill the the perturbation in a span-wise, and it will perform what we call a dancing wave. So it will be like waves. It goes like this, and that sometimes they go 2D, and then it will be shifted from the other with another phase on the span-wise direction, and then come back, and then it will be like and start toward the 2D waves. And this is how Hassan and I, we call them a dancing waves. I have another animation just for this case, and it's really a small beta. So on the left, it's just the visualization of the interface. And on the right is the interface colored with the concentration of the surfactant. And here is the interfacial surfactant gamma. And as you can see, you have a maximum of here in this part of the waves and minimum. So you will have like a Marangoni playing only in a span-wise direction, and that's why you have this type of dancing motion, because here it's high concentration. With the Marangoni stress, it will diffuse this part of surfactant here in the front, and then it will go like this, and vice versa. Is this type of dancing until destabilization. As you can see here, the maximum, and then it will go 2D, and a second round of a 3D, and this is to the other part of the interface, and then a second, and then 2D again, and it goes. So here it's, I'll say, the major result of surfactant line for falling film in the context of a falling film application. In more, I would say, quantitative result, here I took like 3 snapshots at different time. Here it's the shape of the wave. And as you can see, the red line here is we replotted here, and we superpose it with the stream-wise velocity. So it's massive here, and in the right it's the surfactant concentration in the blue curve, and the Marangoni stress tau. And you can see here the maximum, it's really in the middle, but in another time, the maximum, it's on the side of the domain. See? So maximum in the middle, and then the maximum in the side, and then you will be dancing until equilibrium, and that's what you have. So so I'm going to show you now another example of in a similar way. We can also apply surfactant in the context of elongated bubble. So this is another work also done by Hassan, and there is a paper that just has been published a month ago in Physical Review Fluid. And this is the configuration. Imagine you have like a really long tube, a capillary tube of the size of only 1 millimeter. And inside you have a bubble. It's full of, so it's filled with liquid. And in the inlet, we push it with a quasi-parabolic profile, and this bubble move. And this is the entire domain in the bottom, so really long channel. And this grid here are the subdomain decomposition. Of course, control parameter for this type of application. If it is clean, we use capillary number and Reynolds number. Add in surfactant, we have Peclet, Biot number, the adsorption, dam color number, and of course the elasticity. I'm going to show you a quick animation of what we have here. So this is when you push a bubble. The Reynolds number, it's quite high. It's about 1,000. And you see when the bubble, I mean, comes closer, you have this type of capillary waves only in the back. The addition of the of surfactant. So in beginning, it's everything, it's homogeneous. But all the interface in surfactant has been pushed through the back. And you see here in the back, it's really high concentration. And in the front of the bubble, it's low. It's low, apart really the nose of it. So we're going to come back later. Because there are of circulation. And that's why here in the nose, I mean, the front nose of it, it's not dark blue. Here is, I'll say, a like-to-like, clean versus surfactant. And you see that with surfactant, the bubble has been, is more longer. And if you see the plots here, it's just the shape of the bubble across a slice. So here it's the nose, it's the front, and here it's the back. So you see the difference when you have surfactant, and here we just make a zoom of it. So the plots here in the back, I'll say in the tail of the bubble, we did the surfactant free, which is green. We did the Marangoni free. That means there is surfactant, but without Marangoni. When I say without Marangoni, that means we remove the tangential force from the Navier-Stokes equation, and of course the surface tension will be reduced. So there is surfactant free, surfactant but Marangoni free, and with surfactant. And you see that when you have Marangoni free, it's almost like surfactant free. When you add surfactant, you have here on the right panel, it's the Marangoni stress. And see how the Marangoni stress, you have a peak right on the tail of the bubble. So that means when you are doing a simulation with surfactant, especially when you take into account of surfactant, it's not enough just to reduce the surface tension only. The Marangoni stress plays a key role, because here between the Marangoni free and surfactant, the local values of the surface tension, it's equal, but dynamics is absolutely different. It's really important to take into account the tangential stress on the interface. And of course, so in this example, we vary many parameters, for example, the elasticity number beta, and this is what you obtain. So blue is green, red is beta, is the elasticity 0.1 to 7. Here, more higher is the elasticity, more you rigidify the interface, and less capillary waves you obtain. And of course, less capillary waves you obtain, more I'll say Marangoni stress you have, especially in the back. And of course, so when you vary, you obtain like variation of surface tension along the bubble. Here it's the back, and here it's the front, and you can see the correlation between the effective local surface tension along the bubble, and also the concentration of the surfactant along the interface. So what is important is not only gamma, it's not only the concentration, but also but more specifically the variation, and with this we can also vary other parameters, for example, the Biot number. And the Biot number, when you vary the Biot number, it gives really interesting phenomena, is that the shape of the bubble, it changes drastically. It's not only the suppression of the capillary wave, but it will redistribute it massively along the interface. As you can see, next slide, this is the shape of the elongated bubble for when you vary the Biot number. And in the top here is the concentration of the interface, and in the bottom it's the Marangoni stress. It's the local Marangoni stress that you obtain. And as you can see, it's spread it long over. And this is the wall, and you have a tiny gap. So it's really thin gap between the bubble and the wall. And here it behaves as a quiet flow, really as a quiet flow between the tube wall and the bubble. And here is the top on the right, the type of velocity that you obtain. A quiet flow in this small gap here, and another quiet flow in the red gap that you see here. And this shape also, when you look inside, there are really interesting features. So that's why you see distribution of surfactant here. It's not really minimum here in the Phys. You have this top recirculation. So the Marangoni stress will diffuse the surfactant along the interface, and at the same time creating this type of recirculation zone inside. So all of this, so you find it in the article, but there is also other perspective in this work, which is singularities. So it is not in the article, but this is, I'll say, perspective work that we are doing. We are pushing the bursting, so the elongated bubble with surfactant to really one parameter that involves like pinch-offs and coalescence and such as this. You see here you have a pinch-off of the bubble, and then this bubble, it will also, a satellite bubble will coalesce with the big bubbles. But when you vary the capillary, we can also obtain more intriguing phenomena, which is droplet encapsulated inside the elongated bubble. And here you see the amount of surfactant that it's provided, and this droplet, it will go forward, and then knock the nose here and burst, and then you'll have a type of coalescence, a droplet inside the bubble, and will coalesce with the liquid environment outside. This is for this from D and E, you see the type of coalescence that we obtain. So this thing is not published yet, but this is type of work we are pursuing with ASAN for further papers. So in summary, I will say just for this part, so we see that the addition of surfactant acts as rigidifying the interface and also suppress the capillary the capillary wave. And a really weak surfactant with the small elasticity number, so it dances, so it plays there until it stabilizes. So for the following film, we are also expanding to do this with more, because all what we have done, it's insoluble, so we can add solubility. And this is clown here that you see, it's so it's not a clown, it's the concentration of surfactant when you add this, when you take into account adsorption and desorption. So, and it's really not numerical bugs. So we reperform this so many times with more mesh, we obtain this phase. So if you see in the future a paper with this type of clown, so be not surprised. Another topics we've been dealing amongst with the group, it's also, it has to do with jet flows. So this is the work carried out with Ricardo Constante Amoris, and we have some papers. The jet is so the jet is it's mainly water and spreading toward really viscous oil, and this jet is pulsed. And this is the configuration in the top here. So I put the physical parameter, the density, viscosity, and you can see that you have a lot of, in beginning, a lot of destabilization, atomization, and Ricardo managed to make this type of regime map when you vary the Weber number and the Reynolds number, and you have 4 zones. It's spread here, so as you can see, but the most important is this zone D. But if we zoom to this zone, from the simplest to the more complex, that's what we have. So the simple case I'm going to show you, it's Reynolds 1000, Weber 30, and this is the type of jet that you have, really clean stream, and the field here, it's the azimuthal vorticity component, and here is the axial vorticity component. Clean, okay, everybody's happy. Another regime, it's this type, Reynolds 1000, Weber 100. So it's still clean, but you have a type of droplets inside, and you have a mushroom structure like. We increase the complexity, a higher Reynolds and a bit smaller Weber, you have this type of flow. So it will be like overlapping mushroom, and then you will have a coalescence. But for the extreme situation, sorry, I think I'm, yeah, the extreme situation, and it's Reynolds 6000 and Weber, you have a roll like a head mushroom structure like, and what happened here, it will be rolling and having a layer of fluids until having this type of multitude of drops inside the mushroom like. So you have destabilization Kelvin elements in the core, a lot of unrolling. This unrolling, it doesn't stop, and you have a multitude of layers. I'm going to show you an animation of this. So this is when you are pulsing and exciting. You have like a toroidal liquid, and then it will destabilize and break up inside. And you see the inside of mushroom, it's full of droplet. And what is amazing here in this simulation, that we are dispersing water to a liquid. But what you see here, it's a formation of ligament. At some point, the ligament it will break up, and you also have a lot of a breakup here also in the front. And if we go to more details, this is the evolution of ligaments. In the beginning, you have a spanwise destabilizations, and then azimuthal destabilization. And if you zoom on this as destabilization and you look through the time, that's what you have. You have the formation of the lobe, and then it will stretch and then become a ligament, pinch off, and then you have just a dispersed ligament, and this ligament will retract and will give up to a lot of droplets. And here what you have is a dispersed, so this ligament is a dispersed water droplet in the continuous oil phase. But inside the liquid, inside this jet, what you'll have the dispersed oil droplets, which is the continuous phase, inside the dispersed water jet. So you have two types of droplet. Oil droplets inside the water jet, and the water droplet outside the oil environment. And here you have type of oil droplets inside the mushroom, which is almost all of them. And when you have also in the core here, you have a lobe and you have like a ligament, but inside the jet. And of course, this ligament will break up at some point and give you a droplets. And this is just to show you inside the mushroom. But what I want to show to express here is it's difficult to quantify with a lot of detail, but we are able to provide statistics of droplet from each phase to another phase. And here it's the oil inside the jet, and here is the probability density function of the drop distribution. And here is the water droplets outside the continuous environment. So we have two types of statistic: oil droplets and water droplets. The addition of surfactants will make the things more complex. So it was really important to be able to carry really this type of simulation in clean configuration without surfactant. The addition of surfactant will be more complex. So you add the marangoni stress, and this is the configuration. Here we take just an example of this enrollment type where you have a mushroom and you have of course concentration in the bulks and on the interface, and this is the control parameter just for the surfactant, Biot number, Pickley number, the elasticity, and here it's the maximum pack-in. And this is what we obtain. Here it's the interface colored with the surfactant concentration. And in the top here, it's a clean mushroom, structured like, and in the bottom, it's the with surfactant. And what you can see that with the surfactant, you have bigger droplets. Here, the coloring, it's the velocity magnitude. And in the bottom, it's the surfactant. And what we do here is we try to isolate the mechanism that brings all of this. For example, the elongated ligament, so the retracting ligament, the bursting droplet, the coalescence, the pinch-offs. We try to isolate the mechanism just to understand what is the final output between clean and surfactant. And here, what you observe. This is the statistics when you compare the clean that I showed you before and surfactant. And here it's really the statistics of the oil, of the oil inside the water jet. And when you superpose, this is what you obtain, clean and surfactant. And what you see that the surfactant provides bigger droplets. And the bigger droplets, you really have to do that the way the ligament will break up and will retract. And you see here, it's a ligament. We just isolate like a curved ligament, and we plot with with the Marangoni stress. And you see here is the concentration of the surfactant. It gives you really a in case. So that's what it gives us when we isolate the mechanism of the ligament. We just take we step aside from this jet flow and just study the ligament alone. We used the configuration of the team of Osman Basaran, and this is a really interesting paper, GFM 2006. They studied the retracting ligament. We're doing this 2D, but we take over this work not only to reproduce and understand, but also because the work back in the time in 2006, they weren't able to go beyond any singularities. So we took this work, we did it in clean way, and also with addition of surfactant. This is a ligament, and we go beyond the pinch off. And this is the retraction of ligament when you have, in a clean situation. So this is the configuration. You have the aspect ratio, length over the radius, and you also, the other control parameter is the Zorg. We fix it to a constant value of 10 minus 3, and we vary all the type of surfactant. And here, the picture here, it just, when you take into consideration surfactant, how fused inside. So this is what you obtain when you add surfactant. So remember, before you have pinch off, but if I stop it here, sorry, I think I'll, I'll stop it here. So here, this is where it's supposed to break up if you remove surfactant, if it was clean. But here, it's not the pinch off, it will escape from the pinch off because you have a lot of concentration surfactant in the neck. And then if you have here, so you have a Marangoni stress, and he will push the surfactant from the neck and far from it, and so it will reopen. That's why so it will avoid this type of pinch off. And of course, I provided also to see the concentration inside the bulk of the ligament. So it retracts with the interface, and you have really nice mushroom structures when it retracts. And here, the comparison between clean and in the presence of surfactant, it's really summarized through this picture. In the top, it's clean, and in the bottom, it's contaminated with the interface. And here, it's at the same time, and you see at the same time the clean will pinch off. And with surfactant, you have really high concentration, and then so it will reopen. It will go to pinch off and then reopen. And what will interesting is the occurrence of all vortex breakdown, which are added structures inside the entire domain, outside and inside the ligament. And it's really interesting to locate them. And if we now, as I said here, we studied this just to say why. When you have jet, you have bigger droplets, and the bigger droplet is really had to do with this, because the surfactant suppress the pinch-off, and that's why when you have clean, you have really a lot of pinch-off with small droplets, where the presence of surfactant, you wouldn't know the pinch-off. At least if you have less pinch-off and with bigger droplets. So there are two messages now when you have pinch off. When you add surfactant in any type of multiphase flow. One, it could be playing as rigidification, so suppress all capillary waves, or it will avoid some types of pinch offs. And here I will say it's not all types of surfactant. Ricardo made an entire work and varying all parameter range, like the Biot number, the Pickley number, the elasticity, and sometimes it's pinches and sometimes not. So I wouldn't generalize it for everything, but this is the main, I'll say, the main conclusion, I will say, when you add surfactant. And of course, if we come back to the jet flow again, you have a lot of phenomena. For example, the addition of surfactant, what you will see, you have here, you have a drop that will create it, and then so a drop, it will punch the front interface of the jet, and then it will burst, and then you have a bursting droplet phenomena. So same big simulation with jet, isolate mechanism of bubble. We work the configuration of bursting bubble with a lot of application. So the bursting bubble, it's really a complex situation where you have a bubble reaching an interface and then it will burst. The cavity will collapse and it will create a jet. If you read like articles about the bursting bubble, I mean all the bursting bubble community, in a clean situation, you define a bursting bubble with a bond number and Ornozorg number. But most of the article, they use the Laplace number. So in the left here, it's clean bursting bubble, and on the right, it's the control parameter when you add surfactant. And of course, we try to push our code to the limit. And I would like, sorry, I think there is also like wine industry, alcohol industry, and this is an experiment that I did at home. It just so it's not champagne, but it's sparkly water, and I use my slow motion phone, and this is the type of bubbles when they burst, all the tiny droplet. I'm showing you here, I would like to introduce you to Louis de Funès. This is an amazing actor in France. I'm sure all the French communities who, if there are any French, they know this actor and they will love this film. And they love this film. And I just want to say that this type of bursting, you can use it for some people who like the taste of wine or whiskey or like sparkle drinks. They put the glass through their nose, and this type of tiny aerosol comes to your nose, and this is that you can feel like the flavors of the drink. And of course, we push this to the limit. We are able to burst like 49 bubbles, and you can see here in the bottom. And also here, it's a configuration of 8 bubbles bursting all simultaneously, just to give this type of effects, a lot of bursting bubble. And what I'm showing this picture, because it's really a famous film in France, and this scene, he was able to predict what type of wine, of what type of alcohol he's having just by smelling it or just by the look of it. So it's a lot of application. So if I come back now to the bursting bubble academically, so this is the type of configuration that we do. When you vary the bond number, bigger the bond number, so bigger the bubble will be, and smaller it is. And here it's the variation, like the shape that we can predict as the function of bursting bubble. And of course, we validate our code, because when you have a bursting bubble, you will have a jet, and the length of the jet has been validated. And when you do, and this is the output, when you take into account the surfactant, clean, you have something like 6 droplets, marangoni-free, 7 droplets, and the surfactant, a pure surfactant with this type of control, you have 3 and 4. Here, actually, it's 4, but it will, it's 2 droplets that will be coalescing. And this is the temporal evolution with the concentration of surfactant. And you see, when you have the jet, so the concentration of surfactant, it will burst the cavity, and most of the things will go here. And the jet, it will be really high concentration. So the jet will move upward, but the concentration surfactant with the marangoni trace will push the jet downward. So that's why, if you go back to this, the final jet, it was smaller when you have surfactant. You see? So this is the thing. Another phenomena that occurred, this is also a paper that we submitted, and we also submitted the revision to a GFM, and we also occurred another type of singularity. If I go back again to the jet, you have coalescence. So the other type of coalescence, so we also isolate the mechanism of coalescence, and we run this alone. But this is a really good nature a Nature publication of Blanchet and Bigioni, 2006. The control parameter for just a coalescence, it's the bond number or Onozorg. And this type of control, you have a pinch off. This is how you created the cascade of coalescence. A drop will coalesce and will generate a smaller droplet. And this smaller droplet will coalesce and recreate another smaller droplet. The addition of surfactant, it will end up the spreading, so it will end up the pinch off. And this is the comparison between clean and surfactant just for the coalescence. And here it's the neck, the evolution of the neck. You see, without surfactant, the neck will go to zero. That's mean the pinch off. And here it will reopen when you add surfactant. So in conclusion, I will say, so we try to make really a multi-phase, a multi-scale, and a lot of complex type of multi-phase flow with surfactant, and we isolate the mechanism just to study them more carefully. And with this, I would like to thank Hassan and Ricardo. I can call them future Dr. Hassan and future Dr. Ricardo. They're expecting to do their Viva very soon, this month or in November. And to finish, I will say that what I said, it's not only with surfactant, it was like the adventure to work with surfactant, but we expand this code with the miscible and immiscible fluid structure interaction, and we'll be dealing with aeration. We also have a heat transfer. We were doing chocolate fountain and ebullition, boiling problem. And with this, I would like to thank all my collaborators again, and also Imperial College HPC and Idris, where we perform all the simulation. Thank you very much for your attention.
Well, thank you very much, Lyes. Let me get my video on, and we have time for questions. There was you can either put them in the chat or just switch them.
I will put this here. So do you see my screen again?
Your screen is there, yeah.
Yeah, with the presentation?
Yeah.
Okay, yeah. Where is the chat?
It's all right. I can read them out. Don't worry.
I can't see them. I think when I share my screen, it's a bit difficult.
Yeah, I can read them out. Or just unmute yourselves and ask a question. That's fine. Well, thank you again. It was a very, very interesting presentation. Very, very impressive simulations. There's a question from Nima Abbaspour. It says, why do the surfactants distribute inhomogeneously? I think that's the question.
Sorry, why the?
Yes, you are right. Can you hear me?
Yes, I can hear you.
I have asked, maybe it's a bit a basic question, but what was very fascinating was why the surfactant distributes so fast and it is inhomogeneous. That was my question, because in liquids, how does it distribute so fast when we have these very fast interactions in high Reynolds number?
Yes, I think that is a competition. I think the most important parameter, I will say, it's the Pickley number, because it really gives you the ratio between inertial and the diffusivity. So there is a competition. It depends on Hypically, but also there is, I'll go back to this slide. You have also competition, the adsorption, desorption, and the inertial, as you can see in the build number here. And it's true that it depends on the type of surfactant. If you have, for example, if you have high elasticity, so sometimes the surfactant can diffuse faster than the turbulent. Well, yeah, I think you can have a competition between inertial and the diffusivity. That's what it gives you this. But in our code, we also control this via the time step. We control the simulation with a time step that when you simulate this, we take the minimum time step that occurs for the, we calculate the viscous time step, the capillary time step, the diffusion surfactant time step, and we take the minimum. So whatever what comes fast, the inertial or the surfactant diffusivity, and then able to track it accurately.
Great.
Thank you. Very interesting.
Thank you. Yeah. Andrew Hazel has a question. Andrew.
Hi. Nice stuff. I missed the beginning, so I'm sorry. You may already have said this, but do you have very high surface Peclet numbers? And if so, do you see numerical instabilities of the interface?
No. Yes, we do have a high Peclet number. I think for the we really try to put ourselves following the literature. What is the accurate amount of surfactant you do for ligaments? Really type also the appropriate type of surfactant for bulb. But we do. I think we pushed. I think we were able to push the Peclet number, the maximum up to 500. I think up to 500. But we are also working with the another Peclet of type of 1000, and we don't have any numerical instabilities.
Oh, okay. Yeah.
The resolution is good. I mean,
it's more like 10 to the 5 on the surface, yeah. And then there are definite issues. But you didn't go that high.
I think we did high, but you must know sometimes you can have saturation, and the surfactant on the interface cannot exceed the maximum packing. So there is a numerical, I'll say, block.
Sure.
To this, yeah, but I'm sure we can go to okay. Higher is the Peclet. I think more higher the resolution needs to be. Sure. So for any Peclet we do here, that is the accurate resolution that we have. Yeah.
Okay. Thank you.
Yeah, I mean, I guess following up from that, there will probably be a phase transition, right? If you have very high Peclet numbers and you get stagnant cap regions, you'll get micelles forming and so forth. So, I mean, I guess there is a limitation, and you probably have a lot of diffusion.
Yes. Good question, but at the meantime, the interface will be able to adsorb or desorb. So it's not
right. If you tune those parameters right, that's true.
Yeah.
I think the point is the surface diffusivity can be quite small sometimes.
Yeah, I mean, I always think of it as 0, actually. Well, but it's
right, exactly. So I think the surface Peclet numbers tend to be quite significant.
Yeah, usually the diffusivity in the interface and on the bulk are the same. Through all the literature that we've been through, we made like of all of surfactants. And we put what is the minimum of this, what is the maximum of this, and we made the table, what is the average. So we worked like this, but it's true that I think it needs to be pushed forward. but the code, I think it's stable enough to handle at the same time all types of singularities and all types of surfactant. Maybe I'm wrong, but up to now, we didn't have difficulties of really pushing through some types of limits. Yeah.
Okay. Shusong had a question, and I kind of share part of it too, actually. I'll read it out. It says, are the interfaces sharp? And please, could you say something about tracking the interfaces and handling their topological change? And I guess I had a similar question, because you've got you've got all the forces in the Navier-Stokes, so they live on a manifold, right? I mean, they live on a the delta function, right? They live somewhere there. And then when two of the interfaces collide, what do you do then? How do you solve the gamma equation?
Yeah, well, yes, actually. So what happened is that we solve this in as a single phase problem. So it density and density, diffusivity, viscosity. It's a function of a Heaviside function. Will be one value there. So what happened? We solved the Navier-Stokes in Eulerian grid, as you can see here. But then you have a tracking. You have like Lagrangian grid only on the interface, and the surfactant actually the gamma, it solves only on the interface. The C, it's really a numerical tuning. So when you have two interface coming so close and it's a numerical criterion, we put it like something like 2% of the size of the grid cell. And then there is a local reconstruction, and also a local reconstruction of the interface, and a local redistribution of the surfactant on the pinch off there. You see, so it's here. I'm afraid it's quite a numerical tuning, but this is also the strength of combining the front tracking technique when we deal with surfactant. Yeah, it's really the surfactant. And it has been very well validated, all this type of validation that I'm showing here. Yeah, but with singularities, both coalescence and pinch-off, it's really a numerical criterion based on the size of the grid. It's just a local reconstruction. What we use here, it's not a classic front tracking. It's front tracking followed with followed with a level set. A level set, it's a distant function, positive in one side and negative in the other side. In one phase and negative in the other phase. And the zero ISO value is the location of the interface. So when we need to reconstruct the interface due to the pinch-off or coalescence, so we reconstruct by adding extra point on the zero ISO value. Mm-hmm. So we take with us a level set. We call this a hybrid front tracking level set technique. So this is how we handle this, and there is no numerical tuning for gamma, because gamma, it sticks to the node of the Lagrangian grid. So it's really each element, each triangle has its own gamma.
Mm-hmm. Okay.
Yeah.
So
the mesh on the interface, it's triangle. So and each triangle you have it's a triangle, 3 points, and also its concentration gamma.
Mm-hmm. And that's convected in a Lagrangian way.
Yeah. Yeah.
Right. Okay. So you solve everything on a kind of on a surface that's evolving along with it.
The paper I've shown here, a lot of details are in this paper. You will see a lot of triangles that it's difficult to explain it here, but all the detail really.
Yeah, actually, I'm doing the viva of one of the students, so I'll read the details a lot.
Excellent. Yeah.
So, Shusong, does that answer your question?
Yes. So you have a lot of pinch off and coalesces. So how sensitive is the result to your numerical treatment? Because I assume you can't trace the pinch off to a numerical, they're geometrically kind of you have to say, okay, when the neck is thin enough, then there is a pinch off, and right. So
yeah. No,
so you need to
it's
set up some
not.
numerical criteria. Say, okay, this is a pinch off, this is a coalesce, and
Yeah. Well, we validated the pinch off criteria and also the coalescence. So I'm just showing the pinch off. I don't know if you are familiar with the work of Eggers, like the scaling time of a pinch off. So you have a liquid thread, and when it pinch off, so the neck, it varies like this.
Yeah.
So it does this, but the G12. So this is our numerical validation, and this is the type of thing we obtain. And with the thing that I said before, like the simulation, it's controlled. If you want to carry this carefully, it's the time step that controls everything. So you have a CFL time step, the capillary time step, the diffusivity time step. I mean, many time step. I think we have something like 6 or 7, and we select the minimum of all of them. So if the flow is dominated with capillary breakup, so it will be the interfacial CFL that will dominate. And then all those type of singularities will be done accurately. No problem at all. Actually, this is validated. I don't think I have, no, yeah. Here, just to say that this singularity of the pinch off, there is no problem at all. And if you come back, for example, the animation of the jet, it's a multitude of, even this one, you see there is a multitude of pinch offs.
Mm-hmm.
Oh yeah, this one. You see how many pinch of simile. Yeah. Of course, here the time step varies. It's not the same. It's not constant time step.
Mm-hmm.
Yeah. Yeah. Does it answer your question?
Yes, to some extent.
Okay.
Or I can imagine it's extremely complicated. So.
Yeah.
So the way to confound the French dude's sniffing abilities is to put lots of surfactant on the top of his champagne.
Well, alcohol, it's type of surfactant.
Uh-huh.
It's type of surfactant. So even the wine, because okay, you have concentration of wine particles on the interface and also in the bulk. So yeah, but it's also no. It's really just say the application. Okay, let's bring Louis de Funès again. What is it? Yeah. I don't know if you like some type of sparkly drinks, and well, sometimes you're able to smell like the flavor of it. It's like concentration of particles that comes to your nose with the glass like this, and sometimes it's actually those aerosols that comes to you. But yeah, I think bursting bubble with surfactant really occur in champagnes or alcohol drinks industry. Yeah. Here I'll say it's not. It's quick. It's just a quick simulation, just to say type of application we can do. And even this one, 49 bubbles bursting, and you have 49 pinch-offs simultaneously.
Yeah, it's quite impressive. Great, thank you. Any other questions from anyone? Just I have just one comment. I think you showed one simulation of the mushroom that formed kind of the vortex sheet that formed very quickly, and it was axisymmetric before doing a lot of things. It reminded me a lot of the vortex sheet simulations that Robert Krasny has done. You know, yeah, kind of this without surfactants, of course. Yeah. It was the case where it didn't have a chance to have much of a length. So kind of I think you had some of those as well at the Reynolds number of 7,000 or so. Mm-hmm. Of course, the Krasny simulations are inviscid, so
yeah. Inviscid.
Yeah, those ones. Yeah, the ones on the upper left. They're very, very similar to the rolling up vortex sheet.
Yes. Yeah, I think so. I think we are familiar with this paper, and actually we're inspired just to see the also this type of vorticity, because so you will see in a paper that will be submitted very soon to the GFM. Here it's also in the clean case. This is clean case.
Right.
It's just like a vortex interface matching together, and yeah.
Yeah, that's actually Ludmila just put in the chat. It's a paper with Monica Nietzsche, Krasny and Nietzsche. It's I'm pretty sure it's the JFM or JCP.
Yeah, I'm sure we are familiar with this paper.
But it looks very, very similar to that. Great.
Excuse me, can I ask a question?
Yeah.
Is the surfactant model is already implemented in any commercial or open source software?
I think there are some attempts to do surfactant on open foam.
Okay.
And it's not as effective yet. The surfactant, the difficulty of surfactant that you have to solve in the bulk, but also on the interface. In my knowledge, I would say no, but maybe I'm not sure.
My another question is: did you have the chance to compare your results with experiment?
All the time. I'll say all the time as we can. The jet maybe not. The bursting bubble, yes. I'll say as we can that experiment, yes. For example, this work on the not on bursting bubble but the coalescence. Sorry, going again. Yeah, this is that is Blanchette. They did this coalescence with and without surfactant, but with the surfactant they use a numerical code able to do only insoluble surfactant. So that's why we expanded with the more soluble. But there is always comparison. Here, it's if you see it's the superposition of our interface and the experiment, and the red it's numerical of Blanchette. So it's I mean we always validate our code and always compare with as much of the experiment that we can.
Great, excellent. I think we better leave it there. We ran over a little bit, but that's okay. That's the tradition that Shusong has left for us from the past. It's good to have a lively discussion. So again, thank you very much. Really excellent results, really interesting work. So thanks again.
You're welcome. Thank you very much.
And I'll send you